All right, hello. We're going to today look at a concept called the definite integral. So we are first going to look at the kind of the ideas of calculating area before. We're going to formalize this into this concept called the Riemann sum. So the idea here with the Riemann sum is you have some interval, okay? So you have some interval from A to B, and we're going to break this up into a bunch of little subintervals. And they don't have to be equally sized. Okay, so we have here, I broke it up into 4 intervals. And this is what you call a partition of the interval from A to B. And so we can kind of take, the idea is that you have some sort of function, f of x, right, that over, and we were interested in somehow calculating the area of this thing. Now, you just have to, if you choose some points in each of these intervals, and we go up and calculate the function value at each of these points, okay, and then what we do is we calculate this, we break this up into rectangles where each rectangle is the height at that point. This is what you call a Riemann sum. Okay, so this is a picture. And so the Riemann sum is what you do is you calculate. So when we say delta xi, that's the change. This is like delta x1, and then this distance would be delta x2. This is the distance delta x3, and this is the distance delta x4. So you calculate the area of each of these rectangles. The height is the function evaluated at xi star, and then the width is delta xi. So you add up all of those products, that's the Riemann sum. Okay, so we'll define a definite integral now. So if you have a function that's defined on some interval from A to B, the definite integral is going to be the limit of the Riemann sums as the largest largest of these widths gets closer and closer to 0. So as you in a sense, as you're chopping this, making a Riemann sum with more and more and more and more rectangles. So this is the notation that we use. We say it's the definite integral of the function f from A to B, and so we use this notation to indicate the integral. So this differential dx is like the limit of these delta x's as they get smaller and smaller and smaller and smaller. And so we define this as the definite integral as long as the limit exists. So there are going to be cases when the limit does not exist. And if the limit exists, we say that the function is integrable on the interval from A to B. So if a function is, as long as the function is continuous on this interval, or if the function has only a finite number of only jump discontinuities, so not infinite discontinuities, but just jump discontinuities, then the function is integrable on this interval from A to B. So this is what we're looking for. If it's continuous on the entire interval, or if it has some discontinuities, but there are only a finite number of them and they're jump discontinuities, then the integral is going to exist. So we'll simplify this idea of a Riemann sum, where we're, instead of letting you choose just any point along the interval, let's just take, if you take the intervals to be a regular partition where we're just using where we're just splitting it, into equally sized chunks. A regular partition, we're going to just call, instead of calling it delta x1, delta x2, delta x, whatever, we'll just call it delta x. That's just going to be the regular and the same width of each of these little intervals. And if we use the right endpoint, then we're going to get a simpler definition for the definite integral. Okay, so we'll say that if the function is this is a theorem now, with this more simplified version of the definition of a Riemann sum. So if the function is integral, but its definite integral can be found by taking the limit as n goes to infinity, the Riemann sum f of xi, where xi is going to be the right endpoint, and the delta x, where delta x is this the width of these regular partitions. Okay, let's just try to express this infinite, this Riemann sum, this limit of Riemann sums as a definite integral. So we're going over the interval 0 to pi. What this sum is doing is taking the function xi to the third plus xi times the sine of xi times this delta. So if you put this in a definite integral, this would be equal to the integral from 0 to pi, and the function being integrated would be simply x to the third plus x times the sine of x, and then you'd put a dx there. So this would be the same, this limit of Riemann sums expressed as a definite integral. So this definite integral, the idea of the definite integral, can be thought of as the net area under the curve between a and b. So by which I mean this, if we're doing it a definite integral from here a to b, this area is added and this area is subtracted. That gives you the net area. So as you go through the task of evaluating these definite integrals using Riemann sums, here's a few formulas that'll be useful. So the first three are just the summation of I, the summation of I squared, and the summation of I to the third. You may know the summation of I from 1 to n, but the other ones you may not have seen for a while if you've seen them before. Then also we have these properties. Now the first is that the summation of a bunch of constants of the same constant c, if you add it up n times, well, it's just going to be c times n. If you were to also, when you have the summation of a constant times these values ai, there's varying a1, a2, a3, whatever they are, you can actually, since c is a common factor of every single one of them, you can factor out the value c outside of the summation. Also, the summation, it's a linear operator, so the summation of ai plus bi can be broken up into the sum of two summations. Same thing is true for differences. The summation of the difference, ai minus bi, is going to be the difference of the two summations. Okay, so let's take an example. Let's take the function f of x is x to the third minus 6x. So we're going to first evaluate a Riemann sum for this, taking the sample points to be the right endpoints, going from 0 to 3. So going from 0 to 3 and taking n equals 6, delta x is going to be 3 minus 0 over 6. So that's going to be 1/2. And so the Riemann sum is going to be I equals 1 to 6 of f of xi times this delta x, right? Now this is actually the sum from I equals 1 to 6 of the f of xi times 1/2. Now what we'll have, we have to evaluate these for each of these xi's, we're going to evaluate the function at xi. So we have the first one is going to be at 1/2, and then we have at 1, and then we have 3/2, and then at 2, and then at 5/2, and then finally at 3. And the function evaluated these points. I'm not going to bore you with the calculation. These are the evaluations of the function at these 6 right endpoints. And so what this is going to give us is this is going to be 1/2 times the sum of these. So it's going to be 1/2 times, if you add these all up, you get, so it's 1/2 times negative 2.875 minus 5 minus 5.625 minus 4 plus 0.625 and then plus 9. And if you evaluate this, you're going to get negative 3.9375. Okay, so this would be the Riemann sum with 6 endpoints, or 6 intervals. And so now let's look at the limit. So the limit is going to be the limit as n goes to infinity. This is the limit of the Riemann sums, and it's the summation from I equals 1 to n. The width of the interval is going to be this delta x. Delta x is going to be 3 over n, right? Because you're taking the width of the interval 3, chopping it up to n pieces that are equally sized. And now we take its xi. Just make a little note over here. Xi is going to be 3i over n. So as it goes from when i goes up to n, you'll be at 3, right? So we have 3i over n to the third power, or let me do it like this, minus 6 times 3i over n. And that's going to be our interval. Now let's clean this up a tad. So this is going to be the limit as n goes to infinity of. Now a few things that I can do, but I'm going to first distribute, and then I'll clean up a bit. So this is going to be. Here we've got, let's see, 3i. I'm going to, my 3 over n actually, for the moment I'm going to factor that out because there's no i's involved. Anything without an I can come out front. So 3 over n. And so what we've got here is 27i to the third over n to the third minus 18i over n. We're going to clean this up a little bit more, so we're going to have the summation. What I'm going to do is I'm going to take this limit as n is going to infinity. We've got, let's see, I can break this up into 2 summations. So we have 3 over n times the sum times 27 over n to the third, summation from I equals 1 to n of I to the third minus 18 over n summation from I equals 1 to n of I. Using the formulas that we had just a bit ago, we can write this as the limit as n goes to infinity, 3 over n times, we have 27 over n to the third times n times n plus 1 over 2 minus 18 over n, oops, sorry. Let's see, it's n squared times n plus 1 squared over 4 minus we have 18 over n times n times n plus 1 over 2. All right, now let's evaluate this on the next page. Okay, so this is the limit as n goes to infinity of, we've got 81 times n squared n plus 1 squared over 4 n to the fourth. Sorry, so I am going to distribute the 3 over n to both terms. Right, so I'm going to get 18 over 2 is 9 times 3 is 27, n times n plus 1 all over n times n is n squared. So you'll notice that if we take the limit, because the parts with the n's, really it's just the leading coefficient. We have n the power of n is the same on the polynomial on the top and the bottom. So we really just, what matters is just the leading coefficient. So this is going to end up being 81 over 4 minus 27. And this comes out to be negative 27 over 4. So that's the summation of this which is 6.75. Okay, let's try to evaluate some definite integrals by thinking of the area. Now here we have an integral from 0 to 1 of this function 1 minus x squared. So it's going to actually behoove us to graph this thing out. And what is the curve y equals square root of 1 minus x squared? If you square both sides, you get y squared equals 1 minus x squared plus y squared equals 1. That's a circle of radius 1. Now, this is a circle of radius 1, but the original curve was just the square root, which just means it's the top arc of this. So this circle does actually continue around, but we're only looking at this area here. The area of a circle of radius 1 is pi times 1 squared, but we're only looking at one quadrant of that, so it's going to be over 4. So it comes out to be pi over 4. Now let's take the integral of this function x minus 1 from 0 to 3. Again, let's graph this thing out, and you'll see that the actually, I'm going to have to move the axis up a tad because this is a line, right? And oh, no, I don't have to move it up that far. This is a line that has an x-intercept at -1. And if we go up to 3, then we're going to be at this point here, right? The line is going from -1 up to 3, and so what we want to do is think about the net area. I'm going to put in red the area here, which is -0.5, and then in blue we've got, if we think of it in breaking it up into grids, the area is going to be an area of 2 there. So the net area is going to be 2 minus 0.5, so that's going to be 1.5. That's the area. So when we're approximating using a definite integral using Riemann sums, there's this rule called the midpoint rule that says that using the midpoint of each interval is often better than using the right or the left endpoint. And so we'll give you an example using the midpoint rule to approximate this integral using n equals 5. So the curve looks like this, and so if we're going from this actually we're going from 1 to 2 and splitting up into 5 sections. So we're going to, well, that's roughly what it is. Okay, so the what we'll have is that this delta x is going to be 2 minus 1 over 5, so that's comes out to 0.2. Okay, each of these little sections has a width of 0.2, and so the I'll call it M5, the Riemann sum with 5. We're going to have the midpoints of these are going to be, we have 1 over 10 times 0.2. Oops, I'm sorry. It's 1 over 2.1. So they all have a width of it's going to be delta x times f of x1 star plus delta x times f of x2 star all the way up to delta x times f of x5 star. Now this is actually the delta x's can be factored out, and then it's going to be f of x1 star plus all the way to f of x5 star. Okay. Now the delta x's are all 0.2, and the first x1 is going to be halfway between 1.0 and 1.2. That's 1.1. And then we have 1 over 1.3 plus 1 over 1.5 plus 1 over 1.7 plus 1 over 1.9. Approximately, this comes out to 0.691908. You can round it off to a different number of places. All right, so here we have some properties of definite integrals that'll be handy. So first off, if you take the definite integral from b to a, that's going to always be the opposite of the definite integral from a to b. So flip the bounds, you're going to change the sign. The definite integral from a to a can be thought of, well, if you have a width of 0, you're going to have an area of 0. So that definite integral is always going to be 0. The definite integral of a constant number over the interval from a to b, that definite integral comes out to be c times the range from b minus a. Now the definite integral you can also split. It's a linear operator, so that means you can, the definite integral of f of x plus g of x can be split up into two definite integrals. The definite integral of a constant times a function is you can factor out the constant, and so you can factor that c out, and then you can split up a difference of functions. So the definite integral of f of x minus g of x is the difference of the two definite integrals. And lastly, if you have a function integral from f of x from a to b, you can always split the integral at any point on its domain, at any point c. So this integral from f of x from a to b is the integral from a to c plus the integral from c to b. Now, c, this point c, often you'll pick a point that's between a and b, but this is true for any point c on the domain as long as the function is integrable on the intervals from a to c, or from c to a, depending if c is less, and then from c to b, or from b to c. As long as it's integrable on that interval, then you can split it. So you can actually, it might sometimes be useful to split at a point beyond a and b, but we might see an example like that later on. Okay, so let's evaluate this definite integral from the definite integral of 4 plus 3x squared from 0 to 1. So for one thing, we can split this up into two integrals. So this is the integral from 0 to 1 of 4 dx plus the integral from 0 to 1 of 3x squared dx. And then we have the integral from, we can actually factor we know that the integral of 4 from 0 to 1 is 4 times 1 minus 0, 4 times that range. And we can actually factor the 3 out, 0 to 1, x squared dx. And we then can, we've evaluated this as a 4, and this is a 3. And if you recall from a previous example, actually from the previous, we've actually looked at this in terms of, we evaluated this limit of Riemann sums. It comes out to be 1/3. And so what we get then is 5. All right, now let's suppose you don't know anything about this function f of x, but we do know that the integral from 0 to 10 is 17. We know the integral from 0 to 8 is 12. Now we want to find the integral from 8 to 10. Well, the integral of f of x from 0 to 10 is the integral from 0 to 8 plus the integral from 8 to 10, using the last property that we looked at. And so if this first integral is 17, we're told, this next integral is 12, and so the next integral is the missing part. And so it's simple enough to find that this integral from 8 to 10 must equal 5, right? Okay. So here's a couple of facts about definite integrals. If you know something about the bounds, the limits of I should say the bounds of the function value over the interval from a to b, then you can say something about the integral. So if you know that the function is always non-negative over the entire interval from a to b, then the integral, the definite integral from a to b, is going to be greater than or equal to 0. Because it's going to have a non-negative area. There's no negative parts to subtract, right? Or to add on. Now, if you have two functions, f of x and g of x, and f of x is always greater than or equal to g of x, then the integral of f of x from a to b is going to be greater than or equal to the integral of g of x over that same a to b. And lastly, if you have, and this kind of follows from that, if you have, if you know that f of x is bounded below by little m and bounded above by big M, then the previous fact actually gives you this. The integral of f of x from a to b is going to be bounded below by m times b minus a and above by big M times b minus a. So we'll attempt to estimate this using properties stated above. Well, okay, so e to the negative x squared, we can say a few things about this. We know that e to the negative x squared on the interval from 0 to 1 is, this is a decreasing function. And we know that this is always going to be, it's upper bounded by e to the 0, and it's lower bounded by e to the negative 1. Okay, so this is 1 over e less than or equal to e to the negative x squared greater than or equal to, or less than or equal to 1. And so since this is the case, then that must be the case that the integral from 0 to 1 of e to the negative x squared must be, so b minus a is just 1, so the width of this this integral this interval is 1, so this is going to be less than or equal to 1 but greater than or equal to 1 over e. So this is an estimate of this definite integral using the properties above, but shortly we'll be using derivatives, or I should say antiderivatives, to get more precise with our answers. Anyway, this is all we're going to say about definite integrals for now. I'll do some more practice on this, and I hope you do well. I'll see you in class.